Eric graduated in physical chemistry in Mulhouse, France, and already used IGC during his thesis, which he finished in 1997. But soon after this, he founded Adscientis and dedicated a large part of his life to IGC as such. I personally know Eric since 7 years, and I always appreciate his strong scientific approach, even though it takes sometimes a little bit long to be really perfect. Today, we are business partners, and I really enjoy working together with him. Just one other thing, Eric is one of the fathers of this symposium, and it's therefore my honor to introduce now the first presentation with Eric as speaker and his title, 20 Years of IGC Experience and Learnings. Eric, please, the virtual floor is yours.
Thank you, Ralph, for your kind introduction. My name is Eric Brendle, and I am the CEO of Adscientis. It is my pleasure to tell you the story of my company, going from the motivation to create to some milestones and advances we perform in the field of IGC. It is also a big challenge for me to condense 20 years in 20 minutes. The origin of Adscientis are related to the laboratory of Eugène Papillère and of Henri Ballard. They start to use IGC in 1978 and wrote around 120 papers and conferences related to the application of IGC to different surfaces. They also contribute to the development and improvement of the IGC method. For example, they were the first to propose a method for the determination of the acid-base character of the surfaces. I had the chance to start to do a PhD and a postdoctoral fellow in this lab. During my PhD, I was using IGC to study the surface properties of metal oxide, and I used this opportunity to develop a method to assess the surface nanoroughness. In 2000, we are founding Adscientis with the first name IGC Lab, together with Eugène Papillère, Henri Ballard, and also with Jean-Baptiste Donnet, which is well known in the field of IGC. The starting point is also the request of some company to ask for IGC analytical services. And I'm proud to tell you that this company are still a customer now. But why founding a company active in IGC? Simply because we believe in the huge potential of this technique. This technique is able to provide so many information, and the number of physicochemical parameters that you can measure is very huge. Here you have a list that is even not exhaustive. Moreover, the delivered parameters are directly related to the interaction ability of the materials. And therefore, it is complementary to the other techniques, like microscopy and spectroscopy. To give you a picture of my mind, I will illustrate it with an analogy between a powder and a candidate, a human candidate for a job. Knowing the picture and the curriculum vitae, that means having a picture of the microscopy and the composition of the material, you are not able to determine if the compatibility is good or not. For the human person, you will perform a job interview. For me, IGC is the same thing for the material. You are injecting different probes and analyzing the answer in the form of retention time or peak shape. However, IGC is not a well-known technique, and therefore we started this company with initial goals and idea. If you focus us on the service, we want to democratize IGC, increase the confidence in the measurement, and increase also the application fields. We also wanted to develop IGC productivity by improving the accuracy of the measurement, decreasing the processing time, and also make IGC easier to perform. We also wanted to develop the knowledge bases. That means by developing quantitative structure property relationship between the surface properties and the application. These goals and idea remain still actual. However, this does not mean that nothing was done during these last 20 years. And so I will show you some achievement in the different fields. In 2000, for example, we developed a device that allows the determination or the characterization using IGC of plate-shaped solid. Especially, this was designed in order to measure the specific surface area of these kinds of material. The key element of this device is the Teflon plate in which a chromatographic paste, a calibrated one, is engraved. This ensures sweet-up chromatographic performance and allows this kind of measurement. Applying this to a stained steel sheet, having 10 centimeters square, you can perform finite concentration measurement. This is done here with two different kinds of probe, xylamine and hexanol. Here on this picture, you can see the obtained isotherms, and you can see also that the hexylamine adsorbs much more strongly than hexanol. However, the exploitation using the BET method of this isotherm leads to similar specific surface area. These values are low at 0.07 square meter, which corresponds to around 8 times the explored geometrical surface. You can also take advantage of the high number of experimental points in order to compute this adsorption energy distribution function. And here you can see that hexylamine adsorbs much more strongly because you have much adsorption site having high adsorption energy. And the conclusion of this study would be that the surface has an acidic dominant character. Later, on the request of a customer, we also developed a method that allows the determination of hydrophilic and hydrophobic character of the surface, but also to compute the size of the hydrophilic domains. To perform this, we have developed a protocol which contains several steps. The first step is to determine the water adsorption isotherms in order to determine the specific surface area of the hydrophilic domain, and also to compute or to determine the relative humidity needed to reach a surface coverage of 1, 2, and 3 water monolayers. After that, we are performing measurements using an hydrophobic probe in order to determine the hydrophobic part of the surface, but also by varying the condition in which we are making these measurements. That means changing the relative humidity. We are looking how this hydrophobic surface is decreasing. The computation of the hydrophilic cluster radius is achieved using a model that was developed with the following main ideas. First, the hydrophilic clusters are distributed on a hydrophobic surface. Here you have the illustration of this model. The water adsorption increase with the relative humidity and also increase the size of the hydrophilic domains, like this. In return, this decrease, of course, the remaining hydrophobic surfaces. And this effect is used to compute, thanks to the model, the size of the hydrophilic domain. This is applied here for 2 aerosol type silica. You can see here the decrease of the hydrophobic part of the surface, and this is significant enough to be exploited. The result you get for aerosol A is, for example, for the hydrophilic part, you measure 32 square meter per gram. For the hydrophobic part, you measure 70 square meter per gram. And the size of the cluster is of 1.6. Compared to the other silica, the B, you can state that the size of the cluster of the hydroxyl B is 2 times higher, but the number of hydroxyl group is lower. And so hydroxyl B would more hydrophilic than hydroxyl A would be more hydrophilic than the hydroxyl B. This was measured several times on a lot of samples, and we measure cluster size between 1.2 and 9.4 nanometers. We also developed a method that allowed to detect if your surface is hard or soft. That means if your samples behave like a pure solid, or if there is some mobility. The method is based on numerous experiments. and on the observation that depending on the nature of the materials you investigated, the isomers of octane behave differently. Hence, on pure minerals and clean surface, the lowest interactive probe would be cyclooctane, whereas the most interactive one would be N-octane. For polymers, above the TG, liquids, and polluted surface, isooctane will interact the less, and cyclooctane the most strongly. And we use this different behavior in order to describe the surface state. In this example, we applied this method to a silica that was grafted with octyl-3 toxicilane. Studying the sample with IGC, you will observe a decrease of the surface energy according to the grafting ratio. And the usual conclusion would be the increase of the grafting ratio corresponds to the surface aerophobation. Applying our method, you can place your samples in 3 different domains. The first one, in blue here, corresponds to clean and anaerobe surface. The yellow one corresponds to soft surface, having a behavior like liquid. And you have also the green domain here, where both effects are existing. That means that you have both soft and hard surfaces. And thanks to this method, you can see how the grafting makes that your sample is moving from something that behaves like a clean surface with a slow nano-roughness effects to something that behaves like a liquid film. We also applied this method to study the aging of IPA. The aging has been done at different time points, 1 and 6 months, and we also study the effect of different storage conditions. With classical IGC, you will observe that the surface energy that you measure for the initial state here is of 38 millijoule per square meter, and then the aged samples are more or less all around 45 square meter per millijoule per square meter. With our method, you see that the initial point is in the green domain, meaning that the surface you analyze is displaying some mobility. And this mobility is decreasing because the edge samples are now in the blue domain. And so this would mean that the surface becomes more and more harder and maybe becomes more crystalline. We can also observe the effect of the storage condition. Stored at -20 degrees, you keep the mobility of the surface. At room temperature, you see that after 1 month, the mobility is kept, but after 6 months, you are in a hard domain, a hard surface domain. Increasing the storage temperature, after 1 month, you already in the blue domain. In conclusion, with storage time, the surface mobility decreases and becomes more hard and crystalline, and the storage temperature accelerates this transition. So the last example I want to show you concerns Inolytix. Inolytix is a modular analytical solution dedicated to IGC measurement we developed. This is composed by instrument, robot, detector, specific device, software. And this was created with the following driving ideas: configure high-quality IGC instrument according to your needs, but also to merge the high performance of the analytical GC device with our own IGC knowledge. Of course, we will convert a part of our know-how into smart softwares. And the final goal is to enhance productivity. The 2 last points are requiring the development of an electronic operator. That means a software that is able to perform a part of the tedious task of human operator. And this software is Nucleus. Oops. The tedious task of the operator is to perform accurately the injection, judge when the peak ends. That means when your peak returns to the baseline before performing next injection. In other words, this is a lot of waiting time. How long time to wait? You don't know in advance because it's at what you measure. But Nucleus was developed to do it for you, thanks to a peak detection function. The other capability of Nucleus is to manage simultaneously and independently the measurements on 2 samples. He drives the GC, the PAL robot. The PAL robot is doing the injection, surveys live the signal on both analytical channels, and detects the end of the peaks before performing the next injection of your measurement protocols. I will show you a video how it works. In this example, we first are sampling 8 microliter of vapor of N-octane. This corresponds roughly to 5 nanomoles. Here you inject, and here you have already, oops, the peak. I'll show you again. I stop it here. And so Nucleus is able to detect the peak start during the running of the peak, the maximum of the peak, is also doing the integration of the peak. And after detecting your peak, it looks the moment where the baseline is reached again. And this is done several times independently of the operator's job. And so you can inject several probes, define a protocol with several injection, and so on, make measurement or leave a Nucleus making the injection and the measurement for you. I hope I have successfully met the challenge of summarizing 20 years of existence in 20 minutes. During these 20 minutes, I present you some of your unique achievements in the field of IGC, like the determination of specific surface area of plates, the determination of hydrophilic and hydrophobic surface area fraction, and is also the determination of the mean size of the hydrophilic domain. I also show you the capability of our method to detect if the surface is smooth or hard. That means if you have some mobility at the surface. And also show you the capability of Nucleus or electronic IGC operator with this function that detect the peak ends. Currently, many other developments are running in different fields, and I hope to be able to present you this development in a next symposium. Thank you for your attention and participation.